So I want to start thanking the organizers of this great thematic program, Mathematics of Oceans. And I want to thank you deeply to all the staff of the Fields Institute. Thank you. So, okay, I hope you can come along with me. This is a completely new result. I think from my heart that this is a very interesting result and is kind of a deciding result in physics. You will tell me. So basically, let's start from some accepted statements, according to some people. A strong turbulence implies high nonlinearity. That's when people talk about strong turbulence, they say, oh, this is strong. I have a colleague, I'm not going to mention the name, who says wave turbulence is weak, and I prefer to work in strong turbulence. Okay, so now wave turbulence implies according to Sergei's talk, the first talk of the program of the week was about the small amplitudes, right? Of small amplitudes, you have a small parameter, and you do analytical expansions about the parameter, and also implicitly there is the idea of n-wave resonances, so or maybe quasi-resonant. Some people can still accept that there is a quasi-resonance interactions, but they don't go beyond that. Okay, so all these, of course, these 2 points are kind of form part of the basis of current research, and this talk is not about breaking that down. It's impossible to break it down, right? It's a big giant, so it's not possible. But I have some evidence in some instances, okay, for some initial conditions, for some type of systems, there is evidence against these statements. So the first statement is denied by the discovery of a new nonlinear transfer mechanism that is stronger at intermediate values of nonlinearity. So if you go even beyond that intermediate value, if you go to really, really high nonlinearity, the transfer is not that strong. The efficiency of the transfer is not that strong. And of course, if you go to very, very small values of nonlinearity, the transfer is infinitesimal. But in between, there is the peak of the transfer. Okay? This mechanism favors transfers towards non-resonant triads. So it is essential that the triad that gets the energy is a non-resonant one. So it doesn't work for exactly resonant triads. It is a robust result. It seems to be very robust to any model. So I tried 2 models. I want to show in this talk 2 models. One is the simple ODE model, and the second is just direct numerical simulation without theory. Okay, and in both cases, the effect is seen. Okay, so yes, you can ask questions. This is basically the idea of the talk. So yes, if you wait a little bit, you will see. Yeah. So okay, let's start with a very horrible equation. This is generic equation for a triad system. Okay. Perhaps it is familiar for most of you. I've just included all the possible terms, and I'm implying here the sums imply that I am considering a periodic torus in this case. But this doesn't really matter. You can think of K1, K2 in some discrete grid. It doesn't need to be set 2. This is just for because there's a relation of this problem with pseudo-spectral simulations of PDEs. So that's why we're using this notation. So, okay, in general, for a general system, these equations are valid to the lowest order in nonlinearity. Typically, there's no more terms, and these equations do not need to be Hamiltonian. Okay, so I'm not asking for Hamiltonian structure here, just this system of equations. So these coefficients are arbitrary, basically. Okay, now I'm going to, because the effect is quite generic, I'm going to use only the first term in the sum, just to illustrate, okay, to illustrate what's happening. So, okay, this is the, I'm starting now considering what is small, what is big. So small amplitudes, in the limit of small amplitude where all the amplitudes, the modes b, k, which are complex functions of time, when they are very small, okay, of course, this is obviously, this equation has not units, correct, it's not corrected units, but don't worry, just take it in a small, okay? Small, very, very small. Continue putting them small in your initial condition. You expect, what do you expect? You expect that the phases that are here in the exponential explicitly rotate much faster than the amplitudes. This is the interaction representation. So the fast oscillation of the linear wave has already been taken away in the definition of these quantities b's. Okay? So basically, quantity b is equal to constant in the first order. Okay? Sounds good? You follow me? Now, if you look at this equation, now you can start understanding what is the time scale. Because you have b over t in the left-hand side, and here you have, this is the Kronecker delta, so it doesn't have units. You have v, the coefficients v, right, times b, and coefficient v times amplitude b has the unit of 1 over time. And that's basically telling you what is the time scale in this problem. Okay? So the frequency of the nonlinear oscillations is kind of proportional to the amplitudes. Okay? That's the correct scaling. But the proportionality constant is the coefficient v. Okay? So which is called interaction coefficient, in fact. So what happens is in this limit, when you consider amplitudes very, very small, you have a rotation of these terms. Most of these terms rotate faster, and when you average over intermediate time scales between the time scale of the functions b and the time scale of these rotations, right? You average over that, you get 0. So you get basically no contribution from them. Okay? The exception is here. Okay? This is interesting, of course, but the talk is not about that. But we have perhaps I could mention here that there's a lot of work on exact resonances. Daniel Kartashoa has had some results, analytical results, finding the resonant manifolds. And, well, I have some results recently regarding Charney Hasegawa Mima in periodic domains. They just published. I will show you in the end the reference. But this is irrelevant for the talk, okay? I should perhaps use this. So, okay, so now start increasing the amplitudes, okay? We started with a small amplitude, now increase the amplitude slowly. Like you take your initial condition and you have a dial and you change the initial amplitude, okay? What happens is the oscillation frequency, which I call it gamma now, from now on, typical oscillation frequency of the nonlinear oscillations, right? It starts becoming a bit faster and faster, okay? Until a resonance occurs. Until this frequency that is dominated by, appears in the oscillation of these terms here, these two terms, this product here, they have a frequency gamma, capital gamma, becomes comparable to this quantity. When that happens, okay, this is a hand wave argument. I will be more explicit later. When that happens, you can have 0 modes here, okay? So you have oscillations that cancel, and they give you a constant, okay? So most of the terms in this sum, in this infinite sum, are oscillating fast, but some of them are constant. And then when you integrate in time, when you solve this equation integrating in time, you're going to get a growth, a linear growth. Okay, it's not exponential, but independently of that is an instability. It's a new kind of instability. Okay, so that's basically the mechanism that I'm proposing this time. Some amplitudes will pick up this instability, so they'll start growing linearly in time. Okay, and this is very robust because it doesn't require initial amplitude. If you are familiar with the modulation and instability equations from optics, in that case from quartets, but you can also generalize the idea to triads, modulation stability requires some non-zero initial condition, but small. In this case, you don't need any initial condition. The mode will pick up this energy, okay, naturally, starting from zero.
You need at least in two modes non-zero amplitude.
Exactly. So that's what happens. So what you do in
it's precisely this. So one mode is big, another is small, and because of that, evolution happens.
Okay, I'll explain again. For modulation stability, you need one small guy here and one small guy here, so you get a linear system. Okay, but for this effect, you need just one small guy, and the rest don't need to be small. Okay, so you put some initial condition in your system, right? You put some energy in your system.
And what would you have on the right hand side?
You need one small guy here, basically zero. Okay, some guy which is initially zero, and these guys here are just some other guys who happen to have non-zero amplitude, because I initiate my system with some non-zero amplitude. Okay, I have my initial condition, of course. I have to start from somewhere. It's not the same. It's not the same. I mean, you can call it as you want, right? If, for example, I was discussing with Miguel Honorato last week, and can you believe? Well, Miguel, probably you are watching this. I said that this is that the thing in triads is called modulation stability. It's not? Well, but we call it like that, column, isn't it? It's the same thing. I mean, it's the same effect. It's two small quantities, or three, or whatever, and they just grow linearly. I mean, they grow exponentially because they satisfy a linear system of equations. Okay, so you have, in general, modulation stability can be said in general, it's a system y dot equals a times y, where a is some matrix, some given matrix, and y is a vector. And then you look at the instability of that. You agree with that?
In Fourier space, you just simply have, one carrier wave, right, which is of large amplitude, let's say at k1, and modulation would be at p2. Right? So one big amplitude, one small amplitude.
Yeah.
I mean, both of them are non-zero, right? And
you need two small amplitudes. It doesn't work with only one small amplitude, or does it? One big.
Yeah.
Okay. I agree. Yeah. That's.
It actually means is that you can start growing the instability from zero background. So the left-hand BK is zero initially. Then you still have growth because it's linear growth, and that's not happening, of course, in the modulation instability because there you have exponential growth.
Or it does if you're not back on the eigenvector. One of sidebands can be non-zero.
Yeah.
It's interesting, because this is so obvious to me now, and it will take time for you to understand, but fine.
There's a period of understanding after the solve.
Yeah. Yeah. Thanks. It's not. I'm not trying to offend anybody, but basically, just bear with me a second, and I will show you this is real. Okay. Okay. So I'm going to produce two quantitative studies of this mechanism. One is just a finite dimensional ODE, just to extract all the complication of a lot of modes. Just consider some system of modes. Okay. 4 modes in this case. In fact, as you can see here, it's 2 triads connected via 2 common modes. So it's basically putting some initial energy in a triad, K1, these are wave vectors, K2, K3. Okay? So I don't care about being small or not. I just put some initial energy in this triad. Is it possible to do so? Yes. And then what happens if there's a second triad here connected to this, K4? What will happen is that under central conditions, the energy will go to this second triad, okay? And this guy, this mode initially has 0 energy, but then you just let it evolve, and it will pick up the energy. You can imagine what happens later. I mean, this is basically the initial structure, the initial situation, then you can extend this idea, this as a paradigm for turbulence. You can imagine this process continuing as a chain of events. Yes?
The problem is that such process, theoretically, I mean, I'm not sure, but theoretically, it can you generate another wave, right?
Yes.
The problem is that it can then stop transferring energy because it will be just increasing your K1, going back. So it's not necessarily that generation of new wave will give you transfer of energy.
Yeah. I agree. But this the inverse process depends on several factors. Let me start with the initial process, and then you see what happens. Okay, this system is just an idealization of the whole structure of connected triads. However, this system still conserves energy, and in fact conserves two purely positive definite quadratic invariants. So you can think, for example, if you are doing a model of turbulence in 2 dimensions, this could be the energy and entropy. Okay. So the idea of the work is basically to start with some initial conditions, which are I allow an overall constant to change the initial conditions, but otherwise they are multiplied by a reference initial value, and these initial values can be arbitrary but fixed. Okay. And then what I do is I let this constant free for later. So what happens is there's an energy flowing from source to target triad, and this you will see it's a type of resonance. Then I will do, after that study, I will do numerical simulation. Oh, it's already 20 minutes. Okay, so I think I have to go fast here. Well, this is this triad here. These two triads connected. These are the wave vectors. This is just some details of the thing. I try to not to get lost on the with all these quantities. But if you reduce that big system I showed before, you get just simply this system. Now I'm taking the source triad frequency mismatch as 0 just for simplicity, so I can get the analytical solutions easily. But you can take any source triads frequency mismatch arbitrary, okay? But for this study, I decided to do this. Now, you have 3 interaction coefficients for the first triad and 3 interaction coefficients for the second triad. These interaction coefficients satisfy some relations if you want that the motion is bounded. And I will completely always impose those relations because I want to describe a system where the energy is bounded. I mean, the motion is bounded, okay? This is not about explosive case, okay, of triads. So this is the system, so you have, and these are the initial conditions. So I initiate with this non-zero initial and the fourth mode with 0. So this is an 8-dimensional phase space. It has 2 quadratic conservation laws, easy to derive, and 2 slave variables. So 2 variables depend only on the remaining 6. So in the end, you can reduce the system to 4 degrees of freedom, which is not necessarily integrable. But I impose bondedness, okay? So initially, this is the situation, and assume that this quantity, the fourth mode, remains small for all times. Why do I assume this? Because I want to prove by absurdity that this is not the case. Okay? So I assume that this B4 is small for all times, and I integrate my equations. Now, if B4 is small, I can discard these 2 terms. Okay? Because the other 2 terms are much bigger. Okay? So I basically end up with this system of equations. Let me write it again. So in blue are the equations for the first 3 modes where I discarded the extra terms, and these 3 equations are decoupled. So B1, B2, and B3 satisfy an equation on their own, which is the triad equation, the so-called integrable triad equations. So this equation is well known. Solution is obtained in terms of Jacobi elliptic functions. Okay? Solution is bounded, and the motion is quasi-periodic. It's almost periodic, but the phases have a little bit of precession. And this precession is quite important for the effect, in fact. Now, once you have found this tree, you just integrate this by quadratures, and you find before. And we will see what happens. So, okay, a little bit of the method. You basically write your three functions in the amplitude phase representation, and the modulus are periodic functions, and also this combination of phases are periodic functions with the same nonlinear frequency, which can be computed analytically. This is homogeneous with respect to changes of initial amplitudes. So you change initial amplitude by a semi-constant, and you get that your frequency changed by multiplying by this constant. Now, look at the system. So you found this first solution of this, and then you plug it in here, and then you integrate. So when you plug it in here, you get basically B2, B3, phi periodic, phi 3 periodic. These are all periodic functions with the same period. Plus, you get these extra terms, which are responsible for quasi-periodic solution, which are called precession frequencies. But they are also functions, you can compute them in terms of initial conditions. It's not a problem. You can compute them analytically, and they are proportional to the amplitudes. So here, all these terms in red are basically the omega 2, omega 3 are proportional to the amplitudes, and the periods of all these periodic functions is gamma, which is also proportional to the amplitude. So now we look at this. Well, now we solve this. Integrate from 0 to t. Initial value is 0, so you don't have an extra term. And this is the solution, where in red I show everything that depends on the original triad. This function is a combination, is a complex function that can be computed analytically, which is periodic with frequency gamma. And these two are just this constant I just defined. So if you are in this situation, if you happen to satisfy this equation exactly for some n, then you get an unbounded growth. So the initial assumption that your model before is very, very small breaks down in a finite time. Okay, this means this is basically the effect in this simple setting. Okay, so this is the mechanism of instability. And now, how do you get this equation to be satisfied? Well, it's easy. You just take your initial condition and multiply it by this extra factor. Okay, you just rescale your initial conditions. And then you can see that it's not difficult to compute that for when the amplitude here, A, is equal to this quantity for some n, you have reached a resonance. Okay, so it is very simple to do this in experiment. You just need to increase the dial until you hit 1, you hit 2, you hit 3. Okay, these are all reference quantities. They don't depend anymore on the amplitudes. And this is a property. This is omega 1, omega 2 plus omega 3 minus omega 4. It's completely independent of the initial conditions. Okay? Okay, so I'm going to show numerical solution of this in the Mathematica file. So the details of this will be put in the web page probably. These are the coefficients. I mean, this is all. I mean, this comes from a model of Charlie Hasegawa-Mina. So I'm happy to give you this for you to play numerically. Okay. So some functions, and what I do here is I manipulate some initial conditions, some given initial conditions. Okay, not important. Some initial conditions where they are not real. They have some complex terms, okay? And then I manipulate. So start from very small amplitude. This amp foo that you see there is the A, factor A, okay? So for very small factor A, you get nothing but the motion of the three B1, B2, B3. In magenta here, you can see the amplitude of B4, which remains small, okay? So this is what everybody expects. The limit of very small amplitudes, nothing happens. There's no transfer, okay? increase the amplitude, and now you see some effect, okay? You see some transfer, but it's minimal still. 2, 4. Now you start seeing how energy is transferred. For 6, you get almost 90%, I mean more than 90% of efficiency of transfer. Of course, then you have some, you have Fermi-Pastor-Coulomb kind of mechanism. You get it back. Then you continue increasing the amplitude beyond those numbers, and 40, and then the transfer is arrested basically, okay? And then if you continue increasing, you will not see any difference with respect to this picture. It goes to a kind of asymptotic behavior. But you see that in this case, the efficiency is not more than 20%, a little bit more than 20%, whereas in the middle, the efficiency was quite big. Yeah, please.
Also integrated time between an average in time of the gain of the amplitude for the before model.
No, this is a full solution of the equations, of these equations. It's a full solution of these equations.
The question is, if you average over time, will you get any transfer or not?
Exactly so. Because
It's exactly.
Yeah, but you want me to average inside the equation and change the coefficients?
Over some time. Maybe much time.
Sorry, oops, I made a...
of the larger oscillation theory.
Just multiple harmonics, for example, they are generated and they stay, but they do not transfer energy directly. If they do not show.
Well,
This is the content of energy. These are the slowest scales. Okay, these are the slowest scales. The slow time scales. Okay, these are plots of the interaction representation amplitudes. Right. So this. Now the I don't know what is that plot. Sorry.
Instead of plotting the instant value of the amplitude, you take the average over until the time in which you are of the amplitude. And then, for example, in Fermi-Pastor-Coulomb, you see that they arrange in an exponential order, but you see some structure.
It looks interesting. I mean, if you want to look at time averages, I'm not against that. I'm not against that. We're going to start looking at that, but I have not done it. Okay. Now, these are the predicted values of A at which there is a resonance. And most of them, I mean, you have positive and negatives. If I continue with different values of n, I will just get so small coefficients in front of the time, you know. In my derivation, there is the amplitude goes linearly in time. And the coefficient in front is very small for the n's very big. It's really, really small. It goes like e to the minus n. So really, I need to consider only a few of them. So you can see here, I predict 4.4, 1.8, 1.7, 1.18. So I'm going to go down here. This is an example with the predicted value a minus 1. You get the blue curve. Then if you multiply the a by 10 times that, you get like the highly nonlinear case. And when you multiply by a small number, you get the small nonlinearity case. Now you can do a full plot. You can plot for all values of a within some range the efficiency, which is equal to the maximum percentage of energy transferred. Okay? And you get a maximum at some point. And the predicted value is here. So it's not too good, right? It's not too good. Now, you see the other maximum? It's close to the second predicted value. And here it's not possible to see, but there's another maximum. So, I'm back to slides. So what I do here to understand really what's going on, I introduce a family of systems. Instead of considering just that system, I introduce a factor epsilon in front of the coefficient that I want to be 0. And I consider a family of different systems with the same initial conditions, but with different values of epsilon. And I also allow for varying the initial condition by multiplying by the factor A. Okay? The case epsilon equals 0 corresponds to the integrable system, where I can compute analytically the resonance. Epsilon equals 1 is the full original system for which I don't have an analytical formula. Of course, you can take epsilon greater than 1 and you can see more models. I study the transfer efficiency as a function of amplitude A and the family epsilon. And what I get is this beautiful plot where, as you can see here, this is log A. I have to be log. Okay. The maximum of this curve is just at that cross there, which is not exactly on the level of epsilon equals 1. This is epsilon equals 1. So the plot I showed you previously, remember the plot I just showed you, is just this slice. Okay? Now notice it's about 96% the maximum. This is the predicted resonance. It follows spot on there. Okay? These are different families. Okay? Each line here corresponds to one family of equations. And you can think of them as deformed systems of equations, right, which are close together. Now this is the predicted second resonance, A minus 2. It also follows spot on with this one. Okay, and then A minus 3, you cannot see it here, but it comes from here. Can you see that line here? Okay, so basically what's happening is that the family of systems allows me to continue to find the resonance here and then go up there. So there's more. You can look at this plateau here, where efficiency is kind of high, but not too high. It's kind of 60%. Okay? This plateau, if you compute this formula, do you see that curve there? This curve, everything to the left of, to the right of that curve, satisfies this equation, this inequality. So basically, what's happening is that the well-known concept of quasi-resonances, right, is here. So it is true that if you are in a quasi-resonant system, you kind of have high efficiency, but it also depends on the value of the interaction coefficient. If your interaction coefficients are too small, then you follow in this region where nothing happens. Okay? So it's kind of very interesting. What else? These resonances here, you can follow them. You can follow the peak here, and it will go this way to the resonances in epsilon. So there's even a structure, a dependence, the delegate dependence in terms of what epsilon means is the ratio between the source and the target interaction coefficients. So there's a rich structure here. Hold on. No? Fine. Okay. Now, what is the nature of the instability? This is a 3D plot. The same plot of previously, okay, but the height plot, okay, where you can see more clearly what's happening. Everything is coming from here. These are the predicted resonances. It's coming from here. It's a ridge, which is quite stiff. It's to the left of the ridge is kind of smooth, and to the right, boom, it falls very abruptly, sharply. And this is a great result. There's an idea of persistence of invariant manifold, which is an unstable periodic orbit. I just found this periodic orbit numerically. I cannot prove that it's periodic analytically, but I don't care because I believe in my numerics. So if you just put yourself there, this is epsilon equals 0.1, but you can do it for any value of epsilon in this region. You just search for you move your A until you hit this high efficiency. You move a little bit, but just a tiny little bit to the to higher value. So you go from there, you get this curve. A little bit higher, you get a periodic solution. I can confirm, I have data. All the quantities are periodic, except for the phases that are quasi-periodic. Okay? And then you move a little bit still to the right, and then you get this behavior. So it goes back. So you see, you have a lot of transfer here, and then you have no transfer here. Okay, so this is very interesting, and I computed again numerically the Lyapunov exponents of this unstable periodic orbit. Because of the counting of degrees of freedom, remember we have 4 degrees of freedom. The system originally is volume preserving, so the sum of the Lyapunov exponents is equal to 0. Now the Lyapunov exponent along the periodic trajectory is 0 by construction. So you have 3 Lyapunov exponents non-zero, and the sum is equal to 0. I find numerically a ratio like that. So 2 of them are negative, -1 and -2, and the third is positive 3. So there's one unstable manifold and a one-dimensional unstable manifold and a two-dimensional stable manifold for this periodic solution. So somehow what happens is you start from your initial condition and you kind of have you have a plane from which you arrive at this solution, and then boom, you escape along one direction. And that escape gets you there. Okay, now simulations of the barotropic vorticity equation. I have videos here, so please wake up. And pseudospectral resolution 128, 128, initial conditions at concentrated at larger scale. So I have a bunch of modes at a small wave number. I put some energy in them, and I just let it evolve. I don't have here the pictures for the spectra, but the spectra is very nice and so on. I put some dissipation. Well, this Brenda Green has done these simulations. We put some dissipations just to make sure that if entropy goes to smaller scales, it will get dissipated there. So somehow what we are measuring here is how efficient is the transfer of entropy to smaller scales as a function of the initial value of amplitude. Okay? So I'm going to show you the videos in a second. This is the result of 3 simulations. The only difference between them is the initial condition by the rescaling factor. Nothing else. Okay? All the rest is the same. So when the rescaling factor is very, very small, this means you are in the linear case, right? No transfer occurs. When you increase a little bit the scaling, you get this curve, this blue curve. So entropy gets dissipated, okay? At the
Initial conditions you integrate.
I said before. So it's you have your wave spectrum, your wave kx, ky, okay, and you put some initial modes here, okay, and then you integrate the system, and you have dissipation here, okay, somehow something like that. Okay, so you see that the loss of entropy is due to the fact that entropy went to this region where it gets dissipated. Okay? By integrating k squared phi. Yeah, the initial condition is basically centered here in a compact support in k space. Okay? Yeah.
For what you are is just how it changes for this moment.
No. For the whole entropy is the total entropy of the system, right? The total entropy of the whole system. Yeah, that's what I'm computing. Okay. So this is the curve. This is the entropy of the whole system, which would be conserved if I didn't have dissipation. Okay. Now I do this very carefully. Okay. For each value of A, I compute how much entropy was lost. I continue this. We continue until it saturates, in fact. So then we compute how much entropy was lost, and that's the efficiency. Of course, divided by the initial value. So efficiency is by definition less than 1, between 0 and 1. So for very small values of amplitude, of initial amplitude, there's no loss, so the efficiency is 0. And then you start increasing the amplitude, and you get a peak value. And then you continue increasing the amplitude, and you don't get a lot of entropy dissipation anymore. But you get kind of to a plateau. Okay? So this is the high nonlinearity case where people would say that they would believe that they're doing the fully turbulent case, but it's not. This is where turbulence is strongest. And you can do this for initial conditions. I said you put modes initial energy here, but you also can play with the phases. If you play with the phases just to see if this is robust or not, you get, of course, you get sensitivity. Because you change the initial conditions, but we randomly chosen phases, okay? There are like 20 modes there, and you just put phases, arbitrary phases in there randomly. And you get a different behavior, but kind of the same idea, no? The peak is up there, and then it goes like that.
I don't understand why exactly. Why is the infinite time solution 0 entropy?
No, it's not 0. Sorry.
Why doesn't all the entropy eventually?
Well, there's an argument. I mean, there's also energy going to larger scales. So all entropy cannot dissipate because there is energy. Yeah. There's a sort of argument.
There's some alternative sort of explanation of your efficiency, because rather small nonlinearities, right? The beta effect is important, and you form zonal flows. Zonal flows, stable zonal flows, they will retain entropy. You will have some shear in them. So for high amplitudes, beta term is not important. You have more isotropic turbulence.
Mm-hmm.
And the entropy will cascade and dissipate at small scales. So that, have you tried to see, what happens to anisotropy and zonal flows when you start losing efficiency, when you increase nonlinearity?
We need to discuss that. At the moment, I do not have the answer. Let me show you the videos. So yeah, I know.
Simple question actually. Could you please tell me what is the number of multiple harmonic from your initial spectral peak, which reaches the dissipation region? Second, third, fourth, 10th.
Don't remember that. This is okay. This is 40. Okay, after 230 aliasing, 42, from minus 42 to plus 42. Okay.
And the spectral peak wave number.
These are, Brenda, 5 or something like that.
5.
Yeah.
8 harmonic is already in the dissipation.
I think so. Yeah. Okay. Now, let me show you the video. So, for small initial amplitudes, okay, what you see is basically the dominance of waves, right? You expect to see that, no? Of course, there's a little bit of dissipation, but it's very small. Dissipation is, in this case, when you have a strong vorticity and in smaller scales. So when you see a color, either very, very, very yellow or very dark region with smaller scales, this means you're going to get dissipation. In this case, you see only bigger scales, big blobs. So not actual dissipation. Okay. So for intermediate values, well, for big, let me show you for big. For big values of amplitude, you get the big vortex. It's a big vortex. The vortex is here, centered at this corner. So you have to imagine. Okay. Unfortunately, it was like that. So this is the fully highly nonlinear case where you see, of course, what do you see? You see formation of smaller scales. Okay. This has some efficiency, 30% or something like that. Of course, you see you see formation of small scales. This is highly nonlinear case. So you would call this turbulence. This is the same initial condition, except the only difference with respect to the previous one is I multiplied all the initial modes by the same real constant, but a little bit bigger in this case. Okay. And now if I do intermediate value of constant, what you see is that somehow the vortex gets excited, it goes in the middle, and it gets completely snapped, right? Very quickly. So this is basically the mechanism in the physical point of view is some kind of serendipity effect where the vortex gets snapped. Okay? I don't know how to explain this. My only understanding is that this effect is so robust that it appears in for any kind of initial condition. Okay? If you want to explain this in terms of physical structures, in the physical space structures, that would be interesting, to have an explanation. So I think I'm almost finished. Can I conclude? So, thank you very much. So, okay, conclusions. A robust energy transfer mechanism towards non-resonant triads has been observed and derived analytically with the ODE model, and also confirmed numerically for ODE and for the full PDE. Okay, here I advance some implications. Just, I believe there is a potential in this theory, because if we understand this mechanism of local transfer, local in topological space of triads, not local in K space, okay? Because when you have a triad, you can have connections between completely different scales. But if you work on topological cluster space, it looks local, right? You have flow there, flow there, flow there, flow there, and all is a flow along throughout the connected cluster of triads. So maybe this can be used, extended, of course, not the atom model, but something more bigger, okay? It could be understood as a mechanism for why turbulence occurs, because somehow some triads, what we learned from the previous picture is that some triads will be selected. Which triads will be selected? The triads for which this efficiency is highest. So this depends on an interesting combination between the amplitudes of the source triad, the frequency mismatch of the target triad, and also on the ratios between the source and target interaction coefficients. So it's a very complicated mechanism that we are kind of discovering with this. Well, it could explain also to be another mechanism for world wave generation, because it's a strong transfer. Now, if you look at you just looked at the pictures, huh? You saw those pictures, the small scale generated. So, of course, so I think I will finish here. I thank you, and just letting you know that this paper will be submitted in a few hours to archive. So keep in touch. Thank you very much. Right.
Go back to where you started.
Yeah. I can go.
Three-way interaction equations, right? Yeah. The previous one, if you want to show it, the previous one.
That. Sorry. There?
No, the one there. Still one there. Yeah. Right. So let's just consider the case of a Hamiltonian system. Then assume that we have no resonant interactions, because that's the case you were in.
Right.
Resonance.
No zeros here.
Then of course there exists a canonical transformation.
Exactly.
Really very simple expression.
Yes. Yes. Very simple? No.
Yes.
It's horribly long. Yeah.
So I don't understand that connection, because I can't see that in that canonical transformation you have such a rich structure.
Yeah, I thought about that. I thought about that, and it is interesting. I mean, I've been telling people about this.
I know, but these were games.
I've been telling them, okay, guys, this is a theorem. You can eliminate these non-resonant terms. You can go to normal form. But when you do that, you lose information on the physics. Yes or no? No?
That's not the correct.
Okay, fine. Okay, great to have controversy here. But
No, the answer is that you are right. I mean, it will bring you infinitely many terms unless you are weakly nonlinear, right? So.
Yeah, but this equation is only valid for the weakly nonlinear limit. It's only valid for small.
You cannot no, it's considered for finite complex.
Yeah. I don't care.
Expansion at the three-way is given resonance. You have to take into account four-way.
There is an amplitude which is affected. I mean,
Isn't it?
is defined domain, and if the amplitude of your data is bigger than something, then simply we can transform.
Exactly. But okay, that's very important. And in fact, this equation is exact for several systems. For example, CHM. You start from the model, PDA model of CHM, and you get an exact, formal, of course, but exact system of equations, which is exactly quadratic. The nonlinearity has no more terms. Okay?
The Haskell-Riemann equation is just an approximate equation.
Yeah, right.
So nonlinearity.
Fine, but isn't it?
I just would like to hear Janet concerning, by the way, I believe what you were talking about. So, if you perform, say, if you consider derivatives, right? So, the three-wave, you can get three-wave equations also if you cut. So, and even more in the simulations, if you increase the amplitude of the initial wave, so instead of Phillips 8, instead of growth on the Phillips 8, you can get some different growth. The problem is that you will get this resonance which you described, what we call resonance, and it looks like here it's not really resonance, it's just something different. So, but you will get this resonance if your nonlinear frequency shifts, which work as precession frequencies, when you consider that simplified model, you remember when you put the zero before.
Precession frequencies and the nonlinear frequency that work together.
So this is more or less resonance with the nonlinear frequency shift. The problem is that in order to get this resonance, you have to get such high amplitude that you will violate conditions for expansion of the Hamiltonian. I'm not saying that this is true for all the cases, but with gravity waves.
Yeah. But this.
I saw this thing, so if you put there too strong wave, so instead of Phillips 8, you will get some strange structures appearing. So, and this is true. This exists. The problem is that whether it's applicable from the physical point of view.
Right. So if you start from a system which conserves, in this case, I don't ask for Hamiltonian. Okay, no Hamiltonian structure. If you start, right, right,
Node concerning gravity waves and the
right, right. So.
On this, which is it's a question of what does big mean? So you big amplitude, individual coefficient.
No, it's amplitude with respect to.
We need to have a big in terms of a norm. So if I multiply a norm by A, then the norm possibly grows by A. But I also know that at least this equation is scale invariant. It just is a time change. So that
Exactly.
with no change in voltage, it's not real invariant.
It is not invariant under time. No, it's not invariant. You change the value, the coefficient in.
No, it's not. It's just a time change. Amplitude change is just a time change. And if I
No. It's not invariant. These terms.
Scale. Well, otherwise big and small.
Sorry to say.
It's a scale in omega, small omega.
Yep. Okay, let me explain this part, Walter, to you. This term breaks the invariance because this term is non-zero, right? And in fact, this term is responsible for the resonance because this is where you see the breaking of the invariance. When the amplitudes dependent terms are comparable to the linear terms. This is independent of the initial condition, independent of the amplitudes. Okay? So this is basically the answer to your question. When I say that something is big, is when this is much bigger than this term, right?
What I need to have, they're big and small, is a Banach space norm, your favorite one, which is, I guess, which respects the, I guess, I wanted to say scaling, but of course you're arguing with my choice of frequency of it. You haven't told me what the frequencies are, but I need something quantitative. And so a simple change of size of amplitude is not a quantitative measure somehow. So it seems to be an example of a phenomenon, but rather hard to claim universality.
It's not scale invariant, because I mean, you see you scale amplitude, right? You scale your time, but what are you going to do with this oscillating factor?
Yeah. These are given in terms of k. I mean, there's a formula for this. It depends on the physics of the problem, on the parameters.
Element and column, which depends on k, really will be dependent. For example, like in gravity waves, it depends on the k and m product.
So I don't know how that behaves, and it will be different in different models.
Yeah, I mean.
I just want to come with modulation instability, right? So, okay, so of course your system is more general. You can see more general two types. Stability has more special types. Carrier wave modulation plus two sidebands. It's kind of more like symmetrical. But as far as the rest is concerned, mechanisms that we described are already there in the modulation instability. Okay, suppose K3 is your carrier wave, K2 is your modulation, K1 is and K4 your two sidebands, right? So where do you want to start? You want carrier wave, okay, non-zero, and then choose any of the other waves. For example, modulation or sideband. That's it, two waves only. The other track is completely.
I agree.
To fill this with energy, even though the growth is not going to be exactly exponential first, because you are not on the eigenvector. If your eigenvector has all of them to a certain proportion non-zero, small disturbances. But you can start not on the eigenvector. There are two actually eigenmodes. One is growing, one is decaying. So if you start asymmetrically like that, you still evolve and start figuring it out. So you're starting with finite amplitudes, and modulation amplitude starting actually with one finite amplitude and one small amplitude. But that's the only difference.
No, I will explain to you because it's I thought about this and I know what is the difference between the two. But it's so easy that I prefer to explain you later. I agree with your comment that if you increase the amplitude, say for example the gain curve, no, the typical gain curve of modulation instability. Obviously, if you change the amplitude with respect to some parameter, of course, you will move in this direction, and there will be a maximum gain at some point. So the effect is of the amplitude depending effect of growth rate of the modulation instability is also there. But the mechanism I just described is different because it's direct energy transfer. It's not due to this to the linear equation. I will explain to you in a second.
To thank again the speaker.
Thanks.